So now let's look at Bayes' rule. So if you do a Google on Bayesian, which is the adjective for Bayes, you get this. I did this a while back. I got 11 million hits. I bet if you do it now, you get even more. And so Bayes was a minister, British in England, back in the early 1700s. And actually, one of it's worth having reading the Wikipedia page or having to dig around a little bit to find out a little bit more about him. Because why was a minister interested in probability? And what he was interested in was calculating the probability of miracles. So it was a religious, but this was in the time of the Enlightenment, and so there was a debate about rationality in religion. And so he was trying to calculate the probability that the sun doesn't rise tomorrow, as an example of a miracle. So suppose I've observed the sun rising 1,000 days in a row. What's the probability that it doesn't rise tomorrow? So it's worth having a read about that. Okay, so Bayes' rule itself, sometimes called Bayes' theorem, but I'm just calling it. Bayes' rule is a better name, I think. Theorem's too grand a title for it. So if you remember, our chain rule, which just follows from the definition of conditional probability, is the probability of E intersection F is the probability of E given F times the probability of F, right? Now, the probability of F given E is the same as the probability of E given F, right? They're the same thing, because the order in which we take the intersection sets doesn't matter. And that means we can write the chain rule, and we get that's equal to the probability of F given E times the probability of E. Right, so we know those two are equal. So we know this guy and this guy, this guy here are equal. So let's set them equal. And then let's divide through by P of F to get rid of that. So we divide both sides by P of F. So that means then we have the probability of E given F is the probability of F given E, P of E, P of F. So what's Bayes' rule doing? So first of all, it trivially just follows from the chain rule, right? It's just and this is how, if you need to remember it, just remember the chain rule. Remember this, the fact that the order doesn't matter, and just drive it. That's what I do. You don't need to memorize it. And what Bayes' rule lets you do is flip the order of the conditioning. So you see on the left-hand side the probability of E given F, and on the right-hand side the probability of F given E. So let's just flip back and forth on the conditioning from one way to another. And it turns out that's quite important. So where are we at now? We've defined our conditional probability. We know how to calculate it. We can map between conditional probabilities and unconditional probabilities. That's marginalization. And now we can flip our conditioning back and forth. That's the three big things we want to do. Okay, there's a bit of terminology because Bayes' rule is important, right? And there's a bunch of machinery around it. So there's a bit of jargon that's worth knowing. So this left-hand side, probability of E given F is the posterior. It's called the posterior. The probability of F given E is called the likelihood. The probability of E there is called the prior. The probability of F is called the evidence, although often it's just not called anything at all. So let's look at some examples. Where does that terminology come from? So suppose the event E, let's try and make it concrete, is that it rains tomorrow. And F is the event that it's cloudy today. So what's the probability it's going to rain tomorrow given that it's cloudy today? That's our posterior. So the prior is the probability that it rains tomorrow without knowing that it's cloudy today. So just given that it's any old day, what's the probability that it rains tomorrow? So not knowing that it's cloudy today. So that's before we observe that it's cloudy, that's our guess. That's the probability we think that it's going to rain tomorrow. So that's our prior in the sense, so prior means means beforehand. So it means before we saw that today was cloudy. The likelihood is the probability that it was a cloudy day before it was rainy. So that's kind of after the fact. And then the posterior here is the probability that it's going to be rain tomorrow after observing clouds today. So we take our prior, our P of E, multiply it by our likelihood, which is the probability that it's cloudy, given that tomorrow's rainy. And then we can calculate our posterior. And probability of F is the chance of a cloudy day with no extra information. So PV is the probability that it was a rainy day. Probability of F there is the chance that it was a cloudy day. Unconditional probability. So let's go back to our HIV testing example and try and apply it, because you get quite surprising results. So it's known that we're quite bad at, as humans are quite bad at reasoning about probabilities and risk generally. And so here's an example this is a classic example of how we make bad guesses about what's going on, and we need to stop and think, and Bayes' rule helps us to stop and think. So I'm going to do it for HIV testing. I should have updated it. It should be COVID testing to make it current, or actually another really relevant example is things like dragnet surveillance. If you've got doing, for example, face recognition in crowds, then all of this stuff applies here, but there's a problem with false positives. Okay, so we've got our HIV test, which is correct 98% of the time. That means if you have HIV, 98% of the time it will be positive, 2% of the time it will make an error and say you don't. And it has a false positive rate of 1%. That means you don't have it. If you take the test, you don't have HIV. 99% of the time it says negative, you don't have it. 1% of the time it makes a mistake and says you do. Turns out that 1% can be significant. So 0.2% of the Irish population has HIV. Our event F is that you test positive. Our event E is that you actually have HIV. So our conditional probability we're interested in is now the probability that you actually have HIV given that you were tested positive. And if you started off initially, you'll tend to think, well, it's 98% accurate. So you think maybe it's 98% or something like that. There's a few errors. But let's apply Bayes' rule. Let's actually go through and calculate it. So we're interested in the probability of E given F. So we've got probability of F given E, probability of E, and probability of F. We have to calculate those three quantities. So the probability that you test positive, given that you actually have HIV, is 0.98, right? That's our probability, the accuracy of the test. Our prior, which is the probability that you have HIV, is 0.2%. And remember, 0.2% is 0.2 over 100, so it's 0.002. That just leaves us to calculate the probability of F, which is the probability that you test positive. We already did that, right, with our marginalisation, so we know what that is. Plug in those values, and what we find is it's 0.16. It's way less than 98%. So what's going on here? So that means if you test positive, the probability that you don't have HIV is 84%. That means it's much more likely that you don't have HIV than that you do, even though you've tested positive. And is that surprising? Of course it's surprising. Let's have rather than just looking at the equations are right, but trying to get some intuition about what's going on. Let's plug in numbers. It's a really good policy generally to plug in numbers when your statistics calculations, just to see what's going on. Okay, so the Irish population is about 4.5 million. 0.2% of that is about 9,000 people. So about 9,000 people are HIV positive. The test detects 98% of them as being positive. So 9,000 times 0.98 is 8,820. So of the 9,000 people, it's going to say all but 80 of them it will correctly detect as positive. 80 will say are negative and make a mistake. Okay. Now, so far so good. Now, is this false positive rate of 1%? That means people who don't have HIV will be told have a positive test incorrectly. So so there's 4.5 million minus 9,000 is the number of people who don't have HIV, and we expect 1% of those to be positive. So that means there's about 45,000 false positives. And you can see now, if you test whole population, you get 8,800 true positives. So that's people who have HIV who get a positive test. But you get 45,000 false positives. That's people who've got a positive test but don't have HIV. And if we look at the fraction, so if there are 45,000 over 45,000 plus 800, we get our 0.84, which is the number that Bayes' rule gives us. And you can see the problem here is when you do, that's why I was mentioning face recognition in a crowd or dragnet surveillance. If you do large-scale tests where there's only a small number of positives, suppose you're looking in a crowd for criminals, there's not that many criminals out there, right? It's a small percentage. And your tests, you make mistakes when you do your face recognition. You incorrectly say someone looks like a criminal, but they're not. Because you're testing everyone, you're going to make tons of mistakes, tons of false positives. And they'll drown out the true positives, these ones here. And so all of these are false accusations. And so that's all this problem with false positives, which is what we're seeing for HIV, but it applies directly to dragnet surveillance with, for example, face recognition or just general stuff on the internet, or monitoring on the internet, or accusing people of being terrorists or criminals, whatever. When you're doing population level surveillance, this problem of false positives gets to be really serious. Now, 1% false positive rate is quite a good level, right? That's a pretty good test. That's an accurate test. Face recognition and so on doesn't achieve anything like that, right? It would be a 5 or 10% false positive rate. So you can imagine correspondingly the scale of the errors. And that's a fundamental problem with all of these things that it's important to keep in your mind and understanding what's going on. We can do another example with spam detection. I plug in some numbers. It's the same example with different numbers. You can list dramatic. I'll let you check that one. Let's finish up with quickly with another example. This is a very famous example. It's its own Wikipedia page, and it's a terrible example. So it's about 20 years ago. And so this is in the similar vein to the fact that if you do large-scale testing, small numbers of false positives can drown out the false positives in the population can drown out the true positives. So there's another way that you can make mistakes, which is if you're comparing two really unlikely events. And so here, so Sally Clark was accused of killing her two babies, 11 weeks and 8 weeks. And there was an expert, since completely discredited and struck off, who said that the probability of two children in the same family having sudden infant death syndrome, so that means dying randomly, was 1 in 73 million. And so then the argument went that means there's a 1 in 73 million chance that Sally Clark was innocent. She was convicted, that was upheld in appeal, and she was in jail, right? It was only like 5 years later that it was overturned, and it's counted as one of the great miscarriages of justice, right? And there's a fair bit of competition for that. So what's the flaw in the reasoning here? So it's to do with the conditioning. So suppose our prosecutor has evidence E against a suspect, right? 2 deaths in this case. Now, the thing that we've missed out is the event that the suspect is innocent. So in this case, of Sally Clark's case, E is the event that we have 2 of these sudden infant deaths. And I is the event that she's innocent. And let's suppose the probability that you get 2 deaths, given that she was innocent, is our 1 in 73 million, right? Now that value is wrong, but that's a separate matter, right? It was calculated incorrectly. Let's suppose that's 1 in 73 million. But that's not the quantity we're interested in. That's the probability that the 2 children died given that she was innocent. What we want is the probability she was innocent given they were the 2 children died, right? It's the other way around. We have to be careful about our conditioning, and Bayes' rule lets us flip like that. And the problem is that this the probability of being guilty is really, the probability of both children dying is very rare, and the probability of being a double murderer is also incredibly rare. So you're comparing two really low probability events, and you have to be super careful when you see stuff like that. So let's plug in our Bayes rule. This is the same as before, same expression as before. We can use our marginalization on the bottom there. And let's think about it. So the probability that if, suppose guilt, so that's the complement of innocence, right? So you have the guilty or innocent. So the probability that they both died given that you were guilty, let's suppose that's about 1. So we can plug it in here, right? This is just to make a rough argument. So we're going to plug that in here, right? We already have the probability of E given I, right? That's 1 in 73 million. So what we're interested in is calculating, our probability that she was innocent is the probability of E given I, P of I, times this guy here is about 1. So we just replace it with 1. And so we need to estimate the guilt, so the probability of a double murderer. But we can assume it's small, right? There's not many double murderers. So the probability, 1 minus pi here, is going to be really small, right? So this guy here is super small. And that means this thing here, the top and the bottom, are about the same. That means the probability of innocence is really close to 1, because the probability of the double murder is really low. Being a double murderer is really low. And the probability of both dying when you're innocent is really low. You see if what's happening here is small numbers cancelling out, and it leads you completely astray. And you can have, to give you some maybe more intuition about it, the same sort of argument is, suppose your chance of winning the Irish lottery is 1 in 2 million. I think it's a bit lower than that now. And suppose you've won the lottery. And the question is, well, did you win it by some nefarious means, or did you win it honestly? So here, winning is a rare event, right? It's pretty unlikely. So that's the argument. Well, you've won the lottery. That's a rare event. You must have been guilty. You must have cheated. That's the Sally Clark argument. Whereas you have to actually say, hang on, winning's a rare event. Winning honestly is a rare event, and cheating's a really rare event. And you need to be careful about how you balance the two of those.